Last class we talked about solid liquid separation, several different types of solid liquid separation, and now we will talk about filters, centrifuges, and what it means by filter aids. Okay. So if you look at a material that needs to be filtered, so there are different problems that material can come into. The viscosity could be very high, the solids that's getting removed may have problem because it may form a compressible bed and so on actually. So we need to do some sort of a pre-treatment in order to make the filtration process easier. So the pre-treatment can be different types of pre-treatment. You could heat the slurry so that it becomes easy for filtration, or you can add a coagulating or a flocculating agent so that the filtration is very easy, or we can use something called the filter aids which will prevent the compression of the bed or improve the porosity of the bed so that the filtration process is fast and reasonably good. So these are the three different approaches by which one could perform or improve the process of filtration. So heating, this is the simplest and the easiest method, least expensive of all these methods. It improves the broth handling because when you heat it up little bit, the filtration process is simplified because the viscosity comes down, and the problem is it is not suitable for thermally labile products. That is the biggest problem with the heating. It can also be used as a pasteurizing, especially if you are talking about milk or milk products which needs to be quickly heated up and cooled so that the bacteria dies, then this type of heating method is very good actually. Okay. So for example, if you look at downstream processing of pullalan from certain pullalanase type of organism, so when you heat it up, what happens is all the proteins get denatured, so they precipitate down, but pullalan, nothing happens to pullalan. So generally we can go up to 80 degrees centigrade for 20 minutes. So all the proteins, as you know, are very thermally sensitive, so they get degraded or deactivated, then they precipitate down except pullalan. So if you know the stability of a protein at a certain temperature, then we can heat up slightly below that value so that the proteins which are more thermally sensitive may precipitate down. Next one is coagulation or flocculation. So I did mention about coagulation, flocculation in the previous class, where we are trying to disrupt the electrostatic forces that are present on the surface of fine particles. Because of that, the particles are not coming together and forming larger flocks. So we can add some coagulating agent or flocculating agent. So as soon as you add this, the particles become slightly larger and then it becomes easy for you to filter. Otherwise the particles are so fine, it may be very difficult for you to filter, or you may require a nano filter type of setup. So in order to avoid that, we can add a coagulating agent or a flocculating agent, make the particles to come together so the particles become larger, and then we can resort to an ordinary filtration techniques. Filter aids. What are these filter aids? Filter aids help in increasing the porosity of the bed. It prevents the bed from compression. As you know, if the bed gets compressed, as the pressure increases, then the flow of liquid through the bed becomes impossible, and so at some point of filtration the entire process stops. So we can add filter aid which will increase the porosity as well as it prevents the compression of the bed. So there are natural materials which are added, there are synthetic materials which are added as filter aids. So they are basically inert, incompressible particles. It could be wood pulp, starch powder, cellulose, inactive carbon, diatomaceous earth, rice husk, and so on actually. Say, right, you can have almost 5% of that can be added into that actually. But then it has got disadvantages, many disadvantages, because the clarity of the filtrate is less with large size particles. Certain antibiotics may bind to the filter aids Okay, so when it binds to the filter aid, you are losing the product. You need to do some optimization. That means we need to perform few experiments at different concentrations of filter aid and then see which is the best concentration. Then you are going to have a contamination of this filter aid in the solid. So if solids is a desired product, then obviously this type of approach is not advised. If the liquid is a desired product, then it is okay. So you can add filter aid in two different approaches. One is, first we can add filter aid so that there is a pre-coat that is formed. That is one approach. Other approach is we can add filter aid and the slurry together so that the cake contains the filter aid is deposited on the surface. So if you are adding that, so we can add the feed slurry with the filter aid and the cake will contain both the solids as well as the filter aid. The other approach is you first add the filter aid suspension, so it forms a pre-coat here, and then after that you add your feed slurry. So the filter aid prevents the blockage of the holes in the filter medium so that the liquid flows nicely. So both the approaches are carried out in industrial scale actually. pH adjustment, that is another approach by which we can improve the filtration. Sometimes we can adjust the pH so that selectively you are denaturing some proteins, and once the protein gets denatured they may just precipitate down actually. So for each protein you may have certain pH at which it gets denatured. So we can add tris or acetic acid in the pH range of 4.5 to 8.5. For example, lactic acid up to pH of 3.5 and so on actually. So we change the pH or we adjust the pH so that unwanted proteins get denatured and precipitate. So you give some time, so maybe half an hour or even 45 minutes so that the neutralized protein aggregates settle down, and then you can take out your liquid or you can resort to normal filtration. So these are the different approaches by which one could improve the filtration process actually. Okay, now let us look at some principles on which the filtration is based on. The most important principle I did mention in the previous class, that is called the Darcy's law. Okay, Darcy's law tells you the velocity of liquid through the bed as a function of directly proportional to the pressure drop across the bed. So higher is the pressure drop, higher will be the velocity, inversely proportional to viscosity. If the viscosity of the liquid is high, obviously the velocity is going to be less, and inversely proportional to the bed thickness. If the bed thickness is less, if the bed thickness is more, the velocity is going to be less, and it is valid only when the Reynolds number is less than 5. So you need to always check that out actually. Okay. Now we can use Darcy's law for doing many things. Suppose I am doing a batch filtration and I have a V volume of slurry which needs to be filtered in time t. So dV by dt divided by A will give you the velocity. Okay, so the velocity is equal to 1 by area of filtration, dV by dt, that is the rate of filtration. So now you can equate this with the previous equation of Darcy's law and then do some adjustments and then we can get some very useful relationship. Now there are situations, various situations are there. The filter cloth or filter medium can offer some resistance, or the filter cloth or filter medium need not offer a resistance. So we can have both types of situation. So if another situation is the solids that is getting removed may form a compressible cake, or the solids that are forms an incompressible cake. Okay. So for example, if you take chalk or clay, it may get compressed as you increase the pressure and it may form a compressible cake, so the liquid will not flow. So basically the flow through will be directly proportional to this factor. Incompressible cake, that will not be a problem. So if we have that sort of situation, then we get a very useful relationship. I am not going into the mathematics of it, how to derive that, but you get up with the equation for an incompressible cake. If I have V volume of slurry to be filtered, and if I am applying a pressure of delta P on a filter cloth of area A, okay, this sigma is the specific cake resistance and rho naught is the mass of cake of solids per volume of filtrate. It is almost like a density, right, mass by volume. It gives you time, how long it will take for me to filter a slurry of volume V using a filter of area A when I apply a pressure of delta P, and the viscosity of the liquid is mu and the slurry mass by volume is rho naught, okay. Sigma is the cake resistance actually. So this is a very useful relationship for batch filtration, and we can calculate how long it will take, the time here on the left hand side. This is for incompressible cake, you have to remember. So for compressible cake you will have one more term that may be coming, which will bring in the effect of pressure here. And similarly, if the medium or the filter cloth offers some resistance, then you will have one more term which will include that as well. Okay, so you need to remember that. So when you have the compressible cake, this factor, okay, the resistance will be modified to include delta P raised to the power S, where S is the cake compressibility. It will vary between 0 to 1, okay. So 0 means it is not compressible, incompressible. So larger the number, there is more compressibility. So if you bring in that, then your time equation, that is time required for filtering, will become like this. So you end up with delta P 1 minus S in the denominator here, you understand, delta P 1 minus S, okay. So if S is equal to 0, then we are talking about incompressible cake, this term will go away. So we have this very useful relationship, and we can do a lot of mathematical calculations, which we will see 1 or 2 examples here. Now if the filter cloth or filter medium offers some resistance, then a term gets introduced that is called Rm. Rm is the term which gives you the resistance offered by the filter cloth, okay. So if that is no, if filter cloth does not offer, then this will go away, and we will have the direct old relationship which we saw in the previous. Okay, so how do you find out the whether the filter cloth offers any resistance or not? Okay, so if I plot relationship between volume of filtrate divided by area on the x-axis as against area into time taken for filtration divided by the volume of filtrate on the y-axis, okay. So volume of filtrate divided by area on the x-axis, volume of filtrate, area and time here on the y-axis, and if the line, this straight line passes through the origin or it does not pass through the origin. If it does not pass through the origin, we can say the filter cloth offers some resistance, and this term will correspond to that resistance offered by the filter cloth. If it passes through the origin, then we can say the filter cloth does not offer any resistance. So we can do this type of graphical method to identify whether the filter cloth offers resistance or not, okay. So let us look at a simple problem. It takes 90 minutes to filter a slurry of 1000 liter using a filter of 2 meter square area. How long it will take to filter 100 meter cube of the same slurry with a filter area of 25 meter square. So we have increased the quantity that needs to be filtered, that means V has increased. We have increased the area from 2 meter to 25 meter square. So originally it is 90 minutes, how long it will take? So the cake properties are the same. It is an incompressible cake, okay. The resistance offered by the cloth is also 0, and we will assume the same driving force. So all you have to do is use the original equation, time equation, where there is no compressibility factor or where there is no resistance offered by the cloth. 1000 liters, 2 meter square area, so we can calculate the remaining factors like sigma and rho naught, and then substitute that in the second equation and calculate the time. That is what we have to do, okay. So take this equation, in the first case you have 90 here, we have 1000 liters here, we have 2 meter square here, okay. So we can calculate that T A square by V, those remaining terms are going to be constant, okay, and then use that in the second equation, and we know V as 100 meter cube, which is 100 into 1000, and we know area as 25 meter square, okay. So we substitute them and we calculate the time. That is what we have to do for the identifying how long it will take to filter 100 meter square, and that is what we are doing, okay. So 90 minutes is the first case, 2 is the area, 1000 is your volume, The second case I do not know the time, I know the area 25 meter square, I know the volume which is 100 meter cube, 1 meter cube is 1000 liters. So, I put it, I get 5760. It is a very useful way when I am going scaling up, I want to find out how long it will take to filter larger volume, how long it will take if I increase the area, and so on actually. So, all I am using is this equation, and then I am doing all the calculations. Okay. Now, next one is a rotary drum filter. So, I had talked about it here before also. So, there is a vacuum, so the slurry gets sucked, that means the solids is coated outside because only the liquid flows through, the drum is porous, and then there is a washing that is taking place here. If there is any impurity which can dissolve in the solvent, it gets dissolved and gets sucked in, and then you are drying the material and then it is removing. This is a very continuous process here. So, the filtration generally takes place when the drum is inside. So, otherwise there is no filtration. The remaining level 2, 3, 4 there is no filtration, only when the drum is inside filtration takes place, and we can use the same filtration equation for calculating all the terms here actually. Okay. So, there is a filtration time, washing time, drying time, and discharge time, and only during the filtration time we can use the same Darcy's law type of equation to calculate all the parameters we want actually. Okay. So, during the filtration time we can use the same Darcy's law. If it is a compressible, we use this 1 minus s in the exponent term. Okay. Then we have the centrifuges. There are different types of centrifuges I mentioned. There is a tubular bowl centrifuge where the solids, the slurry comes from the bottom, the solids are thrown out and they form a coat on both sides, and the pure liquid goes out. Generally this is used when the amount of solids are much less, whereas filter is preferred if the amount of solids are in large quantities. Okay. So, we can look at to modeling of this tubular bowl centrifuge also. So, you have, when the solids are moving up, you have two forces that are acting on the solids. One is the centrifugal force which is throwing the solid out, and one is the force along the axis where the bulk of the liquid is flowing. So, if you use these two terms and then write the model, you end up with a very interesting equation like this. The throughput through the bowl centrifuge is made up of the radius, these are the radius of the bowl, and then the omega, that is the angular velocity at which it is rotating, g, and v is the velocity, terminal settling velocity term comes in. So, if I assume that r naught and r1 are almost same, that means it does not form a very thick cake, then the equation becomes very simple. The throughput through the centrifuge is made up of the particle settling velocity v, and these parameters are connected with the hardware details of your centrifuge. R is your radius, L is your length, omega is your angular velocity. So, the throughput depends on two parameters, the particle settling velocity. Again, particle settling velocity, if you remember, terminal settling velocity depends on the physical properties of the solid and liquid, like the density of the solid, density of the liquid, and viscosity of the liquid, diameter of the particle, and the term inside the square bracket is all related to the hardware. Okay. So, this is a very simple and useful relationship which we can do many problems using this. I am going to do one problem soon for you on this actually. Okay. Same thing for disc stack centrifuge, it has got lot of discs here. So, the liquid, the slurry flows from the bottom, solids hits the disc and gets thrown out, and so these walls will be full of solid which can be drained, and the central portion will be the clear liquid which is removed out. So, here again you model this performance, you get throughput is equal to velocity, that is the terminal settling velocity multiplied by the hardware details, which takes care of radius and frequency and angle at which it is the discs are placed and so on actually. So, the velocity here again will depend upon the physical properties of the solid and the liquid, and then the hardware details. Okay, so let us look at one simple problem. A bowl centrifuge is used to harvest cells. The cells are broken so that the diameter reduces by half. So, if the diameter was d, it has become d half. the viscosity has become double, that means the viscosity is mu, it has become 2 mu now. If the same centrifuge is used, then what will be the throughput? Okay. So, now the diameter has come down, the viscosity has doubled. So, only the velocity V has changed, whereas the hardware of the centrifuge is the same. So, we have Q is equal to as velocity into hardware details. Velocity is based on your Stokes law. So, we put in these terms and we can calculate the new Q, and that is what is requested here. What will be the throughput? Okay. So, throughput is function of particle settling velocity in hardware. Okay, particle settling velocity, if you remember Stokes law couple of classes back I did. So, d square 18 mu rho s minus rho l g. Now, d has become half, so 1 by 4 will come here, mu has become 2 mu, so it become 1 by 8. So, throughput has become 1 by 8, right. So, throughput has become 1 by 8. So, new throughput will be old throughput multiplied by 1 by 8, because your velocity has come by 1 by 8. So, it is a very useful. So, if I am using the same centrifuge for larger particle and then same centrifuge for smaller particle, I need to realize, because particle size has come down, the terminal settling velocity will come down, so throughput also will come down. Okay. So, if the viscosity changes, particle settling velocity will change, so throughput will come down. So, I cannot use the same centrifuge to do both the jobs, larger particle and smaller particle, because the throughput will come down quite a lot. So, you can see just a simple equation, we get a lot of information out of it. Okay, so look at another problem. You have mixtures of bacteria, two bacteria which you need, and it is at a certain fraction 50-50, and these are the properties of these two bacteria given, and I want to know how long it will take for me to filter 1000 liters, okay, using a 5 meter square filter cloth. There is no resistance on the cloth and there is a delta P is 1. So, here what do? You have sigma c, right, mu sigma c rho naught for bacteria 1 is given here, for bacteria 2 is given here, and both are 50-50. So, we can take average of these two as a average mu rho naught c, average mu sigma rho, substitute here and calculate time. So, it is very simple. So, we are taking average of the properties because we are taking 50-50. So, depending upon the concentration we can take that particular weightage and do the calculation. Okay. So, if there are 2 or 3 or 4, we will take correspondingly the mu sigma rho naught in that particular ratio of concentration. Okay. So, we will end up with 6.3 minutes for filtering the mixtures of these two bacteria. Okay, let us look at another problem. We have immobilized animal cells, they are having certain particles here 150 micron, and it has got a density of 1.4 grams. This is separated from the liquid medium in a settling tank. So, you must, I talked about settling tank last class, right. So, it is a cylindrical tank, it has got a diameter of 10 centimeter and it has got a height of 70 centimeter. So, you are supposed to calculate what will be the settling time, assuming that the particle quickly reach the terminal settling velocity. The liquid density is 1, viscosity 1.1 centipoise. So, use Stokes law. Stokes law gives you the velocity is equal to d square by 18 mu rho s minus rho l g. So, rho s is given, that is the solid density 1.04, the liquid density is 1, and then mu is given 1.1 centipoise, diameter is 150 micron. So, you convert all of them in proper units, you will get the velocity. Once you calculate the velocity, the height is given as 70 centimeters. Okay. So, the height divided by velocity will give you the time. So, it will tell you how long it will take for that to settle from top to bottom. Okay. That is what you are doing here. So, you calculate the velocity using, and then tank height by velocity, you calculate the time. So, it will take 26 minutes, actually it will take much longer. We assume that the particles will reach terminal settling velocity immediately, but it will take some time. So, normally if you are running an industry, if you calculate the settling time based on this 26 minutes, you will add about 20-30% extra. Okay. So, you will add another 6-7 minutes, you will say about that, it may take about 35 minutes for the solids to settle down. So, your tank height you can redesign to assume about 35 minutes. Okay. or you will leave much slightly longer, so that the solids get enough time to settle. Of course, there are some assumptions here, because if the slurry is very thick, that means if the percentage of solids is very high, we cannot use Stokes law. Generally Stokes law is valid only when Reynolds number is less than 1. If it is much larger, there is going to be solid interaction. So there is simple terminal settling velocity equation of Stokes law is not valid in that situation. So what you do is you can recheck to see whether your Reynolds number is really coming down to less than 1. You all know Reynolds number is diameter of the particle, velocity at which it is flowing, density of the liquid divided by viscosity of the liquid, okay, and check whether Reynolds number is okay. If it is not okay, then obviously the Stokes law is not really valid, but even in an industrial scale you can add some extra safety margin as it is called, and then we can give more time for it to settle. Now what is a throughput? Throughput is nothing but the tank volume divided by batch cycle time, okay. The batch cycle time is actually 26 minutes, right, and what is the volume? Volume is nothing but it is a cylindrical vessel, so pi d square by 4 into height divided by time. Diameter is 10, so you are making it 10 square, and the height of the tank is 70 centimeters, so you are multiplying 26 minutes is what you calculated, so it is coming down to 211. But if you are assuming instead of 26 minutes settling time 35 minutes settling time, you will divide by 35, not 26, so your throughput will come down. So you have to keep that in mind. So if you give some safety margin, you need to correspondingly reduce the throughput. So this is the ideal, or this is the best you may think of achieving, but if you are going to increase this particular time because of safety margin, then your throughput will also come down. So today we did some very useful problems using two simple equations. One is the Stokes law equation, which tells you the velocity at which solids settle down in very dilute solutions. So it is dependent upon the diameter of the particles, the density of the liquid, density of the solid, and viscosity of the liquid, okay. That is very useful in centrifuge type situation. It is useful in settling in gravitational situation. The next one, we use Darcy's law. Darcy's law is very useful to look at filtration. We can calculate what is the time required for filtering a slurry of volume V given an area A. You can have two situations. One is the compressible solid bed, other is incompressible solid bed. If you have compressible solid bed, you bring in the term called compressibility, if you remember S, okay. Otherwise if it is incompressible, you do not bring in that term, okay. Then we said that the filter medium, that is filter cloth, offers some resistance, Rm we said, and filter cloth does not offer resistance. So we can bring in that also. So by incorporating all these, we can get a relationship for time in the left hand side. We can calculate how long it will take to filter a slurry of volume V if given an area of filtration A with certain properties of the slurry and certain delta P and compressible or incompressible, okay. Then in a centrifuge, we looked at the throughput through a centrifuge is a product of the settling velocity into hardware details. So if I use the same hardware, that means if I use the same centrifuge, if I am having particles of d size and if I am using a particle of d by 2, how will the throughput change? If I have a viscosity of the medium mu and if the viscosity of the medium doubles 2 mu, what will happen? So the settling velocity changes, that Stokes law will change, but the hardware will not change, so that will affect the overall throughput, okay. So simple equations, but lot of useful knowledge we got from these simple equations, okay. Thank you very much.